Today we delve into the fascinating subject of 3I Atlas, an interstellar object that orbits the Sun, characterized by its remarkably bright blue hue and strange horizontal and vertical accelerations that have yet to be explained. These unusual signals suggest the potential for an impact whose nature may not be entirely natural. The primary question is whether 3I Atlas can withstand the proximity to the Sun without falling apart, and if it does endure, what might that information reveal about its genuine structure and origins? On October 29, Atlas reached perihelion, encountering radiation levels as high as 770 watts per square meter, a significant stress test in terms of heat and force, capable of obliterating most small celestial bodies in the solar system, unless their structural integrity is exceptionally robust. This event gave rise to several crucial scientific inquiries. Would the object deform, crack, or partially vaporize under such intense radiation? Does it consist of materials with extraordinary durability or a high proportion of rare minerals? And if 3I Atlas remains unscathed after such a severe test, could we be witnessing an extraordinary natural occurrence, or perhaps a construct aligned with principles of which terrestrial science remains largely unaware? Keep watching, as what follows is bound to astonish you. For those intrigued by the enigmatic nature of 3I Atlas and eager for more captivating cosmic tales, please hit the like button to show the universe you're tuned in. Each click aids our pursuit of the unknown. Leave a comment below and tell me where you're watching this from. I'm curious about the different corners of the world engaging with this mystery alongside me. Some researchers have even proposed a conspiracy theory. Should 3I Atlas continue to demonstrate persistent accelerations that clash with traditional cometary models, we may be confronting a much larger interstellar enigma than initial surface observations indicate. As it nears the Sun, 3I Atlas reveals a peculiar form of gravitational acceleration that cannot be solely attributed to gravity or conventional dynamics. The observed acceleration implies that if it were a purely natural object, it would have had to lose roughly 15% of its overall mass to generate the required thrust. This figure is not a random guess. It is grounded in the expected velocity of volatiles that may sublimate and escape the comet's surface due to the heat of perihelion. In this scenario, the outer mantle material would have to evaporate significantly, suggesting that a considerable portion of the core itself may have been lost to result in the acceleration we've observed. If such intense sublimation were indeed the case, it would offer astronomers a golden opportunity to analyze the object's chemical makeup and ascertain whether 3I Atlas is a regular comet or an undocumented anomaly of interstellar material. Nonetheless, there exists another possibility that is still quietly explored within the research community. This anti-gravitational acceleration might stem from an active control mechanism. If 3I Atlas is equipped with propulsion systems, these could resemble classic rocket engines, akin to the technology developed by humans, or perhaps even some unknown advanced technology potentially linked to extraterrestrial civilizations. Notably, hypothetical models involving propulsion show that 3I Atlas's acceleration levels are relatively consistent with energy-conserving operational modes, pointing toward a trend of deliberate navigation rather than the random behavior of conventional evaporating comets. It is this convergence of documented observations and theoretical models that continues to anchor 3I Atlas at the fragile intersection of empirical science and mysterious unknowns, where every minute detail could blur the lines between natural phenomena and interstellar artificial intelligence. A few days following perihelion, new images from ground-based and space telescopes unveiled an astonishing detail. 3I Atlas appeared to possess at least 7 narrow, well-defined jets ejecting at various angles, some directed straight toward the Sun. This behavior is atypical for natural comets, which generally have wide and disorganized jets, not the sharply directed streams observed in 3I Atlas. Images obtained in the days that followed further baffled researchers, revealing that these jets were not merely short-lived, but had formed extensive structures stretching for millions of kilometers. The jet directed toward the Sun reached approximately 1 million kilometers in length, while the jet on the opposite side extended for 3 million kilometers, resulting in an unusual and asymmetrical double tail. Such a concentrated and stable energy distribution compelled scientists to reevaluate traditional physical models. Was this simply an eruption caused by the intense sublimation of surface materials? Or were we observing an entirely different control mechanism, potentially operating in a push-pull optimization reminiscent of artificial steering systems? The asymmetry present on a scale of millions of kilometers offers a significant clue. If these jets are not random, but rather shaped with purpose, 3I Atlas could be executing some sort of intentional orbital correction. This notion does not eliminate the possibility of natural causes, but rather introduces a compelling gray area where both cautious and bold theories of interstellar technology become topics of conversation within the scientific community. As a jet from 3I Atlas travels toward the Sun, it faces the immense pressure of the solar wind from about 1 million kilometers away. For any jet to survive, it must maintain an extremely high density to navigate through the immense speed of the solar wind, which is 1,000 times swifter than the sublimation speed of about 400 meters per second. This significant speed differential implies that to endure without being dispersed, the jet's density needs to be at least 1 million times greater than that of a natural cometary jet. According to Professor Avi Loeb's estimate, the total mass transported through these jets is around 5 billion tons, a seemingly preposterous figure for a small comet that would have to sublimate such an enormous amount of material under even optimal conditions, particularly if it used the most readily sublimable form of ice, CO2 ice. The active surface required to achieve this would need to encompass an area of at least 20 kilometers in size. This creates a fascinating scientific paradox. The initial size estimate of 3I Atlas based on Hubble data is significantly smaller than what sublimation simulations propose. If the estimates regarding the jets are accurate, we are then confronted with two completely opposing but equally astonishing scenarios. Either 3I Atlas is a natural object whose scale and dynamics have eluded current comet models, or the jets are not resulting from natural sublimation but arise from some kind of active technology that modulates and ejects thrust in ways beyond our current comprehension. Moreover, the mass being transported in the billions of tons and the capacity to navigate the solar wind raises crucial questions, hinting at a pattern or action we have yet to fully decode. Data and observations linked to 3I Atlas signal a critical turning point in science, presenting two divergent scenarios, each carrying profound implications. In the case of the natural comet hypothesis, 3I Atlas is likely to have experienced or is about to encounter fragmentation. When a significant object breaks apart into smaller pieces, its overall surface area dramatically increases, thereby accelerating the rate of sublimation and mass loss under the Sun's powerful tidal influence. The fragments will stretch and separate in the upcoming weeks, creating a stream of material, and the gradual evaporation of a sizable portion of mass during this phase will provide scientists with an invaluable opportunity to spectrally analyze the ejected material and uncover the precise chemical makeup of 3I Atlas. Should it prove to be a typical comet, this data could clarify many existing controversies by reinstating the object within the realm of recognized natural models. On the other hand, the technological perspective adds a compelling layer to the story. If 3I Atlas remains structurally intact after perihelion with no indications of persistent fragmentation, and velocity readings suggest that the jets operate with intense thrust, far exceeding the 400 meters per second limit of natural sublimation, then the scenario changes dramatically. An increase in jet velocity by just 1 or 2 orders of magnitude, achievable with advanced human-made ion or chemical propulsion, would drastically reduce the required jet density, implying that the fuel carried would constitute only a minor fraction of the total mass of the spacecraft, were it indeed an actively guided structure. The implications of this technological perspective cannot be overlooked. An interstellar object capable of maintaining its form amidst extreme radiation, emitting high-speed directed jets while consuming minimal fuel, transcends what we understand as natural phenomena. This brings forth the critical question: is 3I Atlas merely an extraordinarily rare natural occurrence? Or are we encountering a sophisticated form of interstellar technology where each jet serves as a precisely tuned mechanism for navigation, far surpassing anything achieved by human engineering? The 3 million kilometer tail of 3I Atlas presents a perplexing temporal paradox. Under normal conditions concerning the outflow rates of cometary material, it would take about 3 months for a jet to extend such a length. However, observational data from the past 3 months reveals no signs of vigorous activity, significant sublimation, or jets large enough to form a 1 million kilometer long structure. This creates an immediate deadlock for the natural comet hypothesis. Even assuming a flow rate 3 times faster than typical, Reducing the time to just 1 month would require velocities that are many times the maximum speed at which volatile molecules can sublimate. The peak thermal speed of molecules during perihelion is only around 400 meters per second, and in truth, larger dust particles and ice fragments generally move at considerably slower rates. Thus, to propel material at speeds well beyond this physical limitation necessitates additional forms of acceleration that sublimation alone cannot provide. This paradox of time and speed remains one of the most intensely debated topics. If there has been no significant activity worth noting over the past 3 months, but the tail remains with its enormous length and apparent density, what energy source could have propelled it so far in such a short span? Some researchers have suggested this could indicate a unique trigger phase where the object accelerates to eject material in an unprecedented, short yet intense manner, an event never before observed in natural comets. Others believe it may signal an active control mechanism akin to a propulsion system engaged periodically, or perhaps on a mission. In either case, the 3 million kilometer tail of 3I Atlas remains a complex enigma. It forces us to reconsider our understanding of the physical limits governing natural comets, or hints at activities current science has yet to fully articulate. The available observational data suggests that 3I Atlas has experienced a notable form of microgravity acceleration, altering its orbit from initial predictions. Strikingly, the extent of this shift is surprisingly small. Over just a little more than a month, the object's orbit has changed by only about 10 times the distance to Earth. Although this number might seem significant, it is trivial when contextualized against the vast scale of an interstellar trajectory. In relation to the mean distance between Earth and the Sun, this deviation is merely a minuscule fraction and does not imply that 3I Atlas will gradually approach our planet. The relevance of this minimal orbital deviation, however, is open to debate. In natural comets, orbital alterations are anticipated when sublimation happens asymmetrically. But in the case of an object with an active steering mechanism, such a minor deviation could indicate a highly sophisticated inertial control strategy, perhaps used to adjust its orbit to prevent potential collisions or maintain a stable orientation in strong solar wind environments. An intriguing technological hypothesis, albeit cautiously speculative, has emerged. 3I Atlas could potentially serve as a mothership that deployed smaller probes before or after its close encounter with the Sun. This scenario aligns with the possibility of subtle steering mechanisms and low levels of orbital variability. However, it's crucial to note that no direct observational evidence supports this notion. To date, no small companion objects have been detected, and no unusual signs suggesting movement have surfaced. The data remains in unsettling silence. Thus, we find ourselves confronting a dual paradox. 3I Atlas has evidently undergone microgravity acceleration, yet the degree of orbital deviation is so slight that it appears disproportionate to the dramatic phenomena observed in the jets. This leads us to a significant question. Is the acceleration being meticulously controlled with remarkable precision, or are we simply overlooking a vital piece of the puzzle that could elucidate how this interstellar entity operates? Regardless of whether the origins of 3I Atlas lie in natural or technological realms, the unfolding narrative continues to present captivating voids within the scientific community. On November 2, a newly identified object was discovered by Gennady Borisov, the astronomer behind the second interstellar object, Borisov. The new object travels at a 110 degrees angle of inclination, which is nearly perpendicular to the orbital plane of 3I Atlas, closely aligned with Earth's orbital plane within 5 degrees. This new object could be unbound to the Sun, possibly having recently been released or originating from the outer edges of the Oort cloud. The two gravitationally defined orbits are no closer than 50 to 100 million kilometers apart. The coincidence of finding a barely unbound near-interstellar object around the perihelion of 3I Atlas is intriguing, though it likely remains a coincidence. However, should this new object be found to be in motion, it may potentially stem from 3I Atlas itself. The U.S. government shutdown has hindered the release of data from the HiRISE telescope, even though the information is available and requires simply to be shared on a common site. The HiRISE team has produced numerous images over the past month, except for those related to 3I Atlas, which they claim need approval from NASA headquarters, a process complicated by the shutdown. Frustration is aimed at scientists who could easily have shared data with their peers and later held press briefings once the shutdown concluded. The question persists. Why would NASA require administrative clearance for anything pertaining to 3I Atlas when they could release images of Mars without incident? This scenario underscores the troubling bureaucratic suppression of scientific insights. Had scientists gained a deeper understanding of 3I Atlas in the past month, they could have analyzed the images and developed new insights to guide future observations. Science thrives on established knowledge, and bureaucratic suppression in time-sensitive contexts is particularly detrimental. The potential ramifications of NASA withholding these images raise questions about institutional interests. It appears that there are factions within the scientific community reluctant to entertain concepts beyond a narrow interpretation of a defunct comet. While individual anomalies can be rationalized, they collectively amount to a significant discrepancy. Predictions made by popular science commentators who are not actively engaged in scientific practice can sometimes resemble AI systems trained only on a single dataset. Comets. Any astronomical occurrence risks being labeled a comet, even if it involves spacecraft that maneuver in an anti-gravity manner and lack the typical cometary tail, as was seen with Oumuamua. This creates a troubling contradiction. Commentators who advocate for the dissemination of scientific knowledge often suggest that the public should maintain a sense of disinterest regarding new developments. They urge the public to endure boredom rather than embracing curiosity. This stance runs counter to the foundational principles of the scientific method, which emphasize humility and learning derived from evidence. Professor Loeb first noted the radio signals linked to 3I Atlas in an essay on Medium, which later garnered media attention. This represented the very first instance of radio signals associated with the object, underscoring the importance of tracking 3I Atlas, a process backed for months. A radio signal was detected containing absorption lines from hydroxyl radicals, oxygen and hydrogen molecules at frequencies not far from the 1977 WOW signal that originated from the same direction. These molecules are typically connected with water-bearing materials, but the exact quantity tied to the absorption lines remains uncertain. This radio signal should not be interpreted as more informative than the detection of carbon dioxide, carbon monoxide, or water molecules identified by the James Webb Telescope on August 6th. Although we are aware that familiar molecules are present around this object, we lack details about their nature. If there exists a form of propulsion system, we are still in the dark about what engines are utilized or what byproducts may be produced. The presence of familiar molecules does not clarify the object's nature unless it has disintegrated, leading us to observe its interior rather than merely its outer shell. Many ice particles could have accumulated on the surface throughout the interstellar journey of any object. In the days and weeks ahead, several factors will shed light on this matter. Aerial images will provide high-resolution views from alternative angles, approaching the object almost from the direction of the Sun, contrasting with the Hubble images captured on July 21, which viewed it at just a 10 degrees angle from the Sun. Subsequent orbits will reveal whether the object maintains its trajectory or presents further anomalies. Evidence of debris will signal fragmentation, while the fate of the jets, whether they persist, intensify, or vanish, will also be vital to understand. As it currently stands, we envision a luminous sphere racing through space, with jets emanating in all directions, not solely away from the Sun as standard comets do, but also directed toward it. This sunward trajectory was clear from the outset. Hundreds of telescopes across the globe will begin monitoring the object this week as it navigates out of the danger zone, where it has been too close to the Sun for safe observation throughout October, remaining less than 30 degrees from the Sun's position. Science is invigorating because we simply observe and learn from the data. Challenges arise when individuals seek to construct narratives prematurely, boasting about possessing the answers unsupported by evidence. This mix of arrogance and impropriety within a scientific context undermines the values of humility and learning from data that should take precedence. Once December arrives, anticipate when 3I Atlas will make its closest approach to Earth, just 6 days before Christmas. We hope it won't bring any unwanted visitors. By that time, scientists aim to ascertain the object's true essence. The next 5 to 10 days will unveil whether it is disintegrating or merely a ball appearing to glide through space. This story mimics a detective narrative, where staying curious is fundamental to uncovering its secrets. Don't forget to subscribe and activate notifications to ensure you won't miss this cosmic moment.